Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll discuss basic PLC instructions. Our objective is to define the make, break, and output enable instructions common in most PLCs, as well as differentiate between electrical continuity as required by traditional hardwire relay-based ladder logic and logical continuity as required by most PLCs. Pay attention to this lecture, as it establishes fundamental ground rules about common PLC program instructions that, if misinterpreted, can be disastrous. This lecture is predicated on the assumption that viewers watch the Introduction to PLCs lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Programmable logic controllers, or PLCs, are programmed using one of 5 accepted languages, where the choice of language depends upon the region where the PLC is employed. The languages include graphical means, like relay ladder logic diagrams, function block diagrams, sequential function charts, and textual methods like statement or instructions lists and structured text. A popular graphical method, ladder logic, mimics the schematics customarily employed in traditional hardwire relay-based ladder logic, including vertical upright power rails and rungs containing instructions in the process sequence. We'll start by discussing 2 input instructions, make and break, and 1 output instruction, output enable, central to programming a PLC using ladder logic. Often a PLC running a ladder logic program is summarized as 3 simple steps. First, the PLC examines the logical states of inputs. Then, it executes the ladder logic program in a sequential, rung-by-rung manner. And finally, delivers appropriate logical outputs. The amount of time a PLC takes to examine inputs, execute the program, and deliver outputs is known as scan time, where scan time is a function of a program's complexity and length. When programming a PLC, it is a recommended practice to minimize the number of instructions and rungs to minimize both the scan time and size of the stored program. Let's first discuss the 2 input instructions, make and break. Alternatively, these instructions are known as XIC, examine if closed, and XIO, examine if open. Another extremely helpful way of thinking about these instructions is if and if not. Before we begin, I will not apologize for the regrettable terms employed by some PLC manufacturers, since it was not I that coined them, but rather historical inertia has dragged these antiquated terms into modernity, quite like the human appendix in U.S. customary measurement units. They are stupid, and I don't like them any more than you do, but we're stuck with them, so we may as well get used to them. There are good ways, bad ways, and extremely convoluted and long-winded ways to differentiate between these 2 important PLC instructions, but I'm going to do my best to make this distinction clear and concise. I am asking you to jettison any baggage you may have with these concepts and just sit back and listen. Long story short, I don't care how you learn this topic. All I'm asking is that you learn it and don't forget it. The instructional methods as presented in this lecture have helped a number of my former students shortcut the nonsense and not second-guess themselves to death. First and foremost, the terms normally open and normally closed are used only to describe the electromechanical nature of real-world field input devices like switches and contacts, and should never, ever be used to describe instructions in a PLC. This push button is normally closed. This push button is normally open. In the deactivated state, as the name implies, the normally closed contact is closed, and the normally open contact is open. In the opposite activated state, the normally closed contact is held open, and the normally open contact is held closed. Similarly, this electromechanical relay has both normally closed and normally open associated contacts. Again, when the coil of the relay is in the de-energized state, the associated contacts are in their deactivated states. The normally closed contacts are closed, and the normally open contacts are open. When the relay coil is in the energized state, the associated contacts switch to their opposite activated state. The normally closed contact opens, and the normally open contacts close. When the coil is de-energized, the associated contacts revert to their deactivated state. These concepts should not be a surprise, and if they are, I am sending you all the way back to the beginning of the Basic Electronics 1 DC Circuit Analysis playlist to begin anew. Look me up again in 3 to 4 months once you've got this concept down. The fundamental confusion regarding the programmed instructions used by PLCs lies in the fact that the make and break symbols commonly used in PLC programs look like normally open and normally closed contacts, and people often mistakenly refer to them in this manner. I must reiterate, the terms normally open and normally closed are used only for the electromechanical nature of real-world field input devices like switches and contacts, and should never, ever be used to describe instructions in a PLC. This symbol is a make, examine if closed, XIC, or if instruction. This symbol is a break, examine if open, XIO, or if not instruction. There are a lot of confusing and tangled methods of defining and differentiating these instructions from each other and between the logical nature of PLC instructions and the electromechanical nature of field input devices, but I will cut straight to the point. PLCs look for logically asserted values, and the two instructions respond differently to the logical states of inputs. Let's first discuss how field devices deliver logical values to PLC input modules. A switch, by its nature, is a digital device in that it can be placed in one of two mutually exclusive binary states, either open or closed, never a little bit of both or halfway in between. When a switch between the source and the input is open, it does not deliver a voltage signal to the input and can be considered delivering a logical 0, low, or false. When a switch between the source and the input is closed, it does deliver a voltage signal to the input and be considered delivering a logical 1, high, or true. The terms 0, low, or false, and 1, high, or true are simply shorthand for the absence or presence of full pilot voltage. For a system using 24-volt DC control voltage, 0 volts would be considered logical 0, and full 24 volts DC would be considered logical 1. In a perfect world, there exists an impassable no man's land between these two digital states, considered invalid. However, in the real world, there's a bit of slop. For example, consider a PLC intended to operate using 24-volt DC that considers control signals between 0 and 5 volts a logical 0, and the values between 15 and 24 volts a logical 1. There still exists an invalid region between 5 and 15. However, the targets for logical 0 and logical 1 are a little larger now, allowing a degree of error due to real-world signal attenuation or poor connection. Different manufacturers may specify different acceptable ranges for logical 0 and 1. Consult the datasheet for your particular device of interest. Note the definitions of logical 0 and logical 1 are rooted in something called positive logic, in that the absence of voltage is a logical 0, and the presence of voltage is a logical 1. The same definition stood on its head could be used in something called negative logic, but this is stupid and confusing. Positive logic is the law, but that doesn't mean people don't disobey it. Be aware of this possibility. Now that we've established some pretty concrete expectations how field input devices deliver logical values to a PLC, let's discuss how the two instructions, make and break, respond to the received logical values. Pay attention because this is important, and I'm only going to say it like 1,000,000 times over the course of this lecture and the next and the next and the next. If a make instruction receives a logical 0 at the input, it does not allow logical continuity left to right. If a make instruction receives a logical 1 at the input, it does allow logical continuity from left to right. In contrast, if a break instruction receives a logical 0 at the input, it does allow logical continuity from left to right. If a break instruction receives a logical 1 at the input, it does not allow logical continuity from left to right. Put this in your pipe and smoke it. Note I'm using the term logical continuity as if a PLC program really established or interrupted current to an output, but this is an analogy only. However, using the graphical ladder logic programming method, it's still very helpful to think of it in this manner. One can think of the left upright rail as a source of logical 1s, i.e. full control voltage. And to logically energize an output on the right, a rung must deliver a logical 1 from left to right. Before we examine these input instructions in greater detail, we need to discuss the output enable, or OTE function. Luckily, this is easy because we're going to use positive logic. If an output receives a logical 0, it is not enabled. If an output receives a logical 1, it is enabled. The output enable instruction looks remarkably similar to a contactor coil and is often illustrated in a PLC program as a parenthesis enclosing the output of interest. Loads hooked to a PLC output include the coils of contactors, the solenoids of fluid power valves, and indicators like LEDs. Normally, a PLC delivers output signals via an electromechanical relay for AC or DC loads, a solid-state transistor exclusively for DC loads, or a triac or back-to-back reverse parallel SCR exclusively for AC loads. Let's assume we're dealing with electromechanical relay outputs since they're the easiest to understand. We'll discuss the peculiarities of the solid-state devices in other lectures. If an assigned output receives a logical 0 via the output enable instruction, the electromechanical relay coil is de-energized and the contact remains in the deactivated open state. Whatever load is attached to that contact is similarly de-energized. If an assigned output receives a logical 1 via the output enable instruction, the electromechanical relay coil is energized and the contact is actuated into the activated closed state. Whatever load is attached to that contact is similarly energized. Now that we've got a basic understanding and definition of the make, break, and output enable instructions, let's examine some simple PLC programs and see how they respond to various field input devices in various actuation states. Consider a 1 input, 1 output PLC using 24-volt DC control logic with a single field input device on input 1 and a pilot lamp on electromechanical relay output Q1. Note the electromechanical nature of the field input device is normally open, and I1 has been instantiated as a make instruction controlling output Q1. Consider the response of this system for two different scenarios. First, when the field input device is in its deactivated open state, and again when it is in its activated closed state. When the field input device is in its deactivated open state, input 1 is receiving a logical 0. Being a make instruction, this means the PLC program does not permit logical continuity from left to right, and the output remains de-energized. When the field input device is in its activated closed state, input 1 is receiving a logical 1. Being a make instruction, this means the PLC program does permit logical continuity from left to right, and the output is energized. The coil of electromechanical relay Q1 is energized, and its associated contacts close. The pilot lamp on output Q1 is energized. Note, some PLC manufacturers offer simulation utilities and the ability to remotely monitor a program in operation. A manufacturer may illustrate those conditions that permit logical continuity and alternate colors are bold, such as I have using pink, while keeping the instruction symbol the same. Let's step it up a notch by performing the same analysis on the same program with only a subtle difference. This time, the electromechanical nature of the field input device attached to input 1 is normally closed. Note the program is still written using a make instruction, despite the radically different electromechanical nature of the field input device. PLCs allow this flexibility, and I must again remind you that the electromechanical nature of the input device has absolutely nothing to do with how that particular input is logically instantiated in a PLC program. Again, let's consider the response of this system for two different scenarios. First, when the field input device is in its deactivated closed state, and again when it's in its activated open state. When the field input device is in its deactivated closed state, input 1 is receiving a logical 1. Being a make instruction, this means the PLC program does permit logical continuity from left to right, and output Q1 is energized. The coil of electromechanical relay Q1 is energized, and its associated contacts close. The pilot lamp on Q1 illuminates. When the field input device is in its activated open state, input 1 is receiving a logical 0. Being a make instruction, this examines the PLC program does not permit logical continuity from left to right, and output Q1 is de-energized. Electromechanical relay Q1 opens, and the pilot lamp on Q1 is unilluminated. Although different field input devices were employed for these two different examples, notice how the make instruction responded consistently with the logical values as received by the input. If the make instruction receives a logical 0 at the input, it did not allow logical continuity from left to right. If the make instruction received a logical 1 at the input, it did allow logical continuity from left to right. The electromechanical nature of the field input device had nothing to do with how the make instruction responded. The make instruction only bases its decision off the logical value at the input. Most students don't have issues with the make instruction and its response to various input devices in various states, since it follows a predictable pattern that closely mimics electrical continuity and traditional hardwire relay-based ladder logic. The break instruction, however, is where folks get lost. Be warned, things are about to get weird.